Welcome to the last video of Chapter 2, Section 2.3 on the length of vector curves. And so the goal of this section is to be able to find the length of an arc along the graph of a vector function. So let's look at the motivation for the formula. We're not actually going to prove the formula. It requires a little bit of an in-depth argument that I don't want to give here. But let's look at the motivation for the formula. So if we give ourselves, we're going to do this in two-dimensional space because it's easier to draw, but the same kind of idea works in 3 dimensions as well. So let's imagine that we have a vector curve. So let's say that this is the curve R of t, and let's give it component functions x of t and y of t. And let's say that I want to have a measure of the distance from some point where t is t1, so r of t1, to some point where r is some other value, or t is some other value r of t2. And so we are looking for the measure of the distance along that arc. Right? So if we were going to walk with a pedometer on us, and we could calculate the distance that we'd walked along that arc. And so the way that we're going to do this is very similar to what you would have done in Calculus 2 when you're looking for area, and that is you're going to split this up into smaller subsegments. So if we imagine splitting this up into n subsegments, and then each of those segments we're going to approximate as a straight line, because the straight line is something that we know how to find the distance of. So let's imagine that we've done that, and we can see, right, if we draw in on each of these straight lines a right triangle. And the right triangle, the base, we'll call delta x, the height we'll call delta y, and so the length of the segment that we're looking for is, using Pythagoras, the square root of delta x squared plus delta y squared. Now we want to add all of those segments up, and so the arc length, which is usually given by the letter s, for the Latin word spatium, which means length, or at least that's what I was always told as to why we call the distance or the length of a curve s. S is going to be approximately the sum. The sum of, we imagine that we've got n different line segments here, and so we're going to add up from 1 to n the delta x squared plus delta y squared. Now I'm leaving off the subscripts of delta x and delta y, and this is all very hand-wavy, but it gives you just sort of an idea of where this the eventual formula is going to come from. Now we don't have a variable t in our expression, so let's introduce one. We're going to factor out a delta t squared from the expression, and if we do that, well, we'd better divide by it. So delta x over delta t squared plus delta y over delta t squared. And that delta t squared, we're going to factor through the root, so the sum from I equals 1 to n of the root of delta x over delta t squared delta y over delta t squared times delta t. Now that might be looking familiar to you from something that you saw in Calculus 2. It's starting to look a little bit like a Riemann sum, and you would remember that you don't want just n of these sub-intervals, straight lines. You want to let n go to infinity, so we'll take this as the limit as n goes to infinity of this expression. Now there is some question as to if this limit exists, and the mean value theorem for real valued functions applied to each component function separately, and then sort of argued that, in fact, the application works all together as one will actually guarantee that this limit does exist. So I'm not going to show any of that. This is just a motivation of this. The limit of a Riemann sum, we remember, becomes an integral from our t1 to t2. The notation changes from delta t to dt, and as n goes to infinity, delta x over delta t, as delta t becomes smaller and smaller and smaller, we get the derivative x prime of t squared plus y prime of t squared. Okay, that is very, very hand-wavy, but that is indeed the right formula. But wait, there's more. That we recognize the sum of the squares of the components square rooted. That is a vector norm. It's not the vector of the original curve. It is the derivative. It is the tangent vector. So the integral from t1 to t2 of the norm of r prime of t dt. And that, in fact, is the correct formula. This, again, not a proof, just sort of a motivation as to where this formula comes from. The takeaway 6 is just the repetition of this formula. The length of an arc along a curve, that is the graph of r of t, from t equals t1 to t equals t2. And a reminder that this works just as well in three-dimensional space as in the plane. S, the arc length, is the integral from t1 to t2 of the norm of the derivative vector r prime of t dt. So let's go and apply that in example 2.3.1. We're asked to find the length of the path along the circular helix. R of t is cos t, t and sine t, from t equals 0 to t equals pi. So we're going to apply this formula directly, so which means that we need, first of all, r prime of t, the tangent vector. So the derivative of cos is minus sine t, derivative of t is 1, and cos t. Next, we're going to need the norm of the derivative. So that is going to be the square root of minus sine t squared plus 1 squared plus cos t all squared. Now, sine squared plus cos squared, that gives us 1. 1 squared is 1. 1 plus 1 is 2. So the norm of the derivative is root 2. Now we want the arc length, so we want the integral from t1 to t2 of the norm of r prime of t dt. t1 is 0, t2 is pi. The derivative, the norm of the tangent vector, gives us root 2 dt, so we are looking at root 2t evaluated from 0 to pi, or root 2 pi minus 0, so root 2 pi units. That is the length of that helical curve from t equals 0 to t equals pi. That is the end of chapter 2. In the next video, we will start chapter 3 on multivariable functions and eventually leading up to partial derivatives.